Hello everyone, welcome to Physics Simplified with Rahul Coaching Academy. Today we'll be discussing lecture 2 from Electrostatics. Today we'll be dealing with all about electric field and electric field lines. Let's first of all understand the topics that we'll be covering during this lecture. We'll be talking about the concept of electric field, what is electric field intensity, and also a few derivations. Intensity due to a point charge, due to a group of charges, and due to a continuous charge distribution. We'll also talk about the rectangular components due to a point charge and what is the physical significance of electric field. There are two more things we'll be dealing. One is electric field lines and what are the properties of electric field lines. So let's get into this lecture by understanding the concept of electric field. Now, what is electric field? It is due to a given charge, it is defined as the field that permeates the space around the charge in which the electrostatic force of attraction or repulsion due to the charge can be experienced by any other charge. Now, what is meant by all these technical lines? For example, let's place a charge here. Right now, if I place another charge here, let's say plus q naught, and let's consider this charge to be positive as well, then we pretty much know by the properties of charges that these two charges are supposed to repel each other because both are like charges. But then if I say that this particular charge is not getting repelled, then this might be one of the reason that because this particular charge is not inside the field of the given charge. Right, so for example, if I just draw a field like this, now this is a space, right? It is a space up to which its force of attraction or repulsion can be experienced. So when we talk about this entire technical statement, what is meant by the statement? That it is basically a space up to which the force can be experienced. Now the force obviously can be attractive as well, it can be repulsive as well. So it is a space around a given charge up to which its force of attraction or repulsion can be experienced. Right now the test charge is not inside the field, so this position is considered as infinity. Anything which is outside the field is considered as infinity. So the moment this particular charge comes onto the field or inside the field, that is when it starts experiencing a force of attraction or repulsion depending upon the polarity of the charges. So electric field is the space around a given charge up to which its force can be experienced. Either the force can be attractive or repulsive. It will solely depend upon the polarity of those charges. Now let's try and understand what is electric field intensity. Now this is really important because this is going to be the core to the entire lecture and the concepts coming ahead. What is the magnitude of electric field intensity? So the magnitude of electric field intensity at any point in the electric field is given by the force that would be experienced by a unit positive charge placed at that point. Now before coming to the formula, let's understand what is meant by the statement. Again, let us consider the same charges again. Let's say now this is my source charge and this is my test charge. This is my source charge at point A, and let's say the test charge is kept at certain point P, and we have to find out first of all what is the electric field intensity at this particular point. Now we pretty much know intensity means the strength. So ideally electric field intensity is giving you the strength of the field. It justifies the strength of the field. That means it will actually tell us that how strong will be the field at that given point. That means if we have to find out the electric field intensity at point P, then we are trying to find out that what is the strength of the field of the source charge at this particular point. So first of all, what will be the force acting with these two charges? The force is going to be the Coulombian force. How do we calculate that? That particular amount of force can be calculated by 1 upon 4 pi epsilon naught into Q1 Q2 by R square. Right, so this is going to be the Coulombian force acting between these two charges. But now this force is acting upon what charge? It is acting upon the test charge, right? Because we are trying to find out the field intensity of the source charge. Always remember, the intensity is always calculated for the source charge with respect to the test charge, right? It is never calculated for the test charge. Yes, it is calculated for the point at which the test charge is situated. But if you have to find out the electric field intensity, it will be always be for the source charge. That means the electric field intensity will give you the strength of the field of the source charge, and it will not be dependent upon the field of the test charge. Always remember this thing. So in that case, if we have to consider the electric field intensity, always remember electric field intensity is represented by E, and it is a vector quantity, because we pretty much know that it will depend upon the position. It will depend upon that what position we are talking about. Thus it will always have a direction. So it is a vector quantity. Then it is given by what? It is given by the amount of force acting on that particular test charge per unit test charge. Amount of force acting on the test charge per unit test charge. This is the Coulombian force. This is the Coulombian force which that particular source charge is applying on the test charge per unit test charge, and that is how we'll actually calculate the electric field intensity. If we go by this particular formula that E is going to be equal to F upon Q naught, in our case the test charge is Q naught, so we are going per unit test charge. So in that particular case the SI unit should be equal to what? SI unit should be equal to Newton per Coulomb, which is actually mentioned here as well. It should be Newton per Coulomb, but there is another unit here, right? This actually should be meters, so it is just represented as uppercase M, but we can also have one more unit for constant electric field. So this will be probably used for constant electric field. Constant electric field. So if there is a constant electric field, then we pretty much use, or rather we can use this unit as well, which is volt per meter. Now how do I acquire this particular unit? It's a pretty simple thing. E is given by what? E is given by F over Q naught, right? This is given by this thing. Now, as per the electric potential concept, we can pretty much write Q is equal to what? Q is equal to V over W. Q is equal to what? It is W over V, my bad. It's going to be equal to W over V, which is work done per unit potential, right? If we just invert this, how do we get this? We can actually get this in form of V upon W, and also work done can be represented as force into displacement, right? And that is how, and this is going to be a vector as well. So in that case we can cancel out the force, and the only thing that will be left with is going to be potential over displacement. Potential obviously is given by volt, and displacement is going to be given by meter, so we can also have one more unit as volt per meter. So that is how we can actually get that second unit as well for electric field intensity. What is that? It is the amount of force acting on a given point per unit positive charge. Do we all understand that thing? Great. Now let's get into the important things, the derivational concepts of electric field intensity. That what are the important derivations that will be associating with this electric field intensity, and at what points? So the first thing that we have is electric field intensity due to a point charge, an important concept. Let's try and understand this. Let's consider a charge plus Q at O. This is our source charge, right? And then we have to calculate the electric field intensity at point P, where another charge plus Q naught is kept. This is our test charge. Obviously we know that both are positive charges, so the force of attraction will be away, or rather force of repulsion will be away from point P, because it's going to be a repulsive force, and intensity obviously will be along that particular force. So we have to calculate the value of this electric field intensity. Now electric field intensity is given by what? It's given by the amount of Coulombian force per unit test charge. So first of all we'll have to calculate that what is the amount of force which is actually acting here. So the amount of force is going to be equal to what? It's going to be 1 upon 4 pi epsilon naught Q1 Q2, which is going to be Q into Q naught upon R square. Obviously the vector along this particular OP, so OP vector is going to be given by what? R vector, because R is the magnitude of that thing. So we can pretty much write it as R square into R cap, where R cap will actually be along this given vector. That will give you the direction of the given vector, right? We can also write this, if I convert that particular unit vector into its vector notation, so we can write this as 1 upon 4 pi epsilon naught into Q naught into R vector. This will be upon R square, and this will be upon R, the magnitude of that particular vector. That means the Coulombian force can be written as 1 upon 4 pi epsilon naught Q into Q naught into R vector divided by RQ. So this will give you the amount of Coulombian force acting at point P due to the source charge. But then what is electric field intensity? Then electric field intensity was F over Q naught. That means E should be equal to what? F, which is 1 upon 4 pi epsilon naught into Q naught into R vector, let me just get the sign correct, upon R cube, divided by what? Divided by the test charge Q naught, and thus this becomes 1 upon 4 pi epsilon naught into Q upon R cube into R vector, and this will actually give us the electric field intensity at a given point due to a point charge. Are we all understanding this thing? It's a pretty simple concept. In the scalar notation, if this is obviously a vector notation, right? Because we are trying to talk about the vectors, and this is going to be a vector notation. If we talk about just the magnitudes, if we are not concerned with the direction, if we are just concerned with the magnitudes, then E vector can be just replaced with E. Then it's going to be equal to what? 1 upon 4 pi epsilon naught into Q upon R square. That means the electric field intensity is inversely proportional to R square. That's an important thing, right? It's going to be inversely proportional to R square. Do we all understand this thing? Let's consider another form of this electric field intensity in a Cartesian plane. Then if we can get absolute relation, and if I have to find out the electric field intensity at point P due to the source charge Q, this is your source charge, this is the source charge, and this is the test charge. Then if you have to find out the electric field intensity at point P, then first of all the Coulombian force is going to be away from that given test charge as per the concept of repulsion. Then going with the same concept, F is going to be equal to what? F is going to be equal to 1 upon 4 pi epsilon naught into Q upon R square. Now first of all, the direction of the vector that we are talking about is this one. This is going to be equal to what? Ri0. I have told you this particular part in when we actually done electric charges as well. This is how we actually represent the notation. Then this is going to be equal to what? This is going to be equal to Ri0 square multiplied with Ri0 unit vector. That will actually give you the direction. If we consider a better notation of that thing or an extended notation of that thing, we can also write this as 1 upon 4 pi epsilon naught Q multiplied with Q into R vector I0 and divided by Ri0 cube, because then obviously we have converted the unit vector into the given vector. This will actually give you the amount of force acting in the vector form. We have done a quite similar variation in Coulomb's law derivation as well, right? And then electric field intensity at that point should be equal to what? It should be F over Q, force per unit charge. So it should actually be equal to what? 1 upon 4 pi epsilon naught into Q into Ri0 vector over Ri0 cube, because we have already cancelled out the Q, and this will give you the electric field intensity at point P. This can further be written in this particular form if we actually get a proper vector notation, that it can be written as into Q. Now how can we write Ri0? Ri0 is going to be R0 minus Ri, which is always final minus initial. So R0 vector minus Ri vector divided by what? Divided by the magnitude of R0 vector minus Ri vector cube, and that will actually give you the electric field intensity at point P in a Cartesian plane, but due to a point charge. Do we all understand that thing? Make sure if you do not understand that thing, just pause the video, rewind the video and understand the concepts again. The next thing that we have is electric field intensity due to a group of charges. That if there are a group of charges, then what is going to be the electric field intensity at a point? So right now this is your test point, right? P is the point at which we have to calculate the electric field intensity due to all these charges Q1, Q2 and Q3. Then the electric field intensity due to Q1 is taken as E1, due to Q2 is taken as E2, and due to Q3 is taken as E3. Then the resultant electric field intensity is given by superposition of the intensities, and the net intensity E, which is going to be somewhere along this particular direction. This is going to be your net intensity, net electric field intensity due to all different charges. Then it's going to be an algebraic sum of all the individual intensities. So it is basically the net intensity. The net intensity will be equal to what? It will be an algebraic sum of individual intensities. So the algebraic sum of the individual electric field intensities will give you the net intensity at a given point, and that will actually give you the electric field intensity due to a group of charges. That means we can pretty much write this as E. If E is the net field, then that will be equal to what? E1. E1 will be equal to what? E1 will be equal to 1 upon 4 pi epsilon naught into Q1 upon R1 Q multiplied with R1 unit vector, or we can just write it as R1 vector. Similarly, plus of 1 upon 4 pi epsilon naught into Q2 upon R2Q into R2 vector, and plus of 1 upon 4 pi epsilon naught into Q3 upon R3Q into R3 vector. We already know how to write these things, right? And we can also write this in summation form, that net intensity E will be equal to what? 1 upon 4 pi epsilon naught summation of, it's going to be Qi for ith particle over Riq multiplied with Ri vector, where I can go from 1 to n to find out the number of particles as n, the number of charges as n, then intensity will be given by summation of all these particles. And that is how we can find out the electric field intensity due to a group of charges over a test point. Do we all understand that thing? It is just the algebraic sum of the individual intensities. Now let's try and understand what is electric field intensity due to a continuous charge distribution. Electric field intensity due to a continuous charge distribution. So now these are the three charge distributions that we had discussed in the first lecture as well. The linear charge distribution, the surface charge distribution, and a volume charge distribution. Let's consider we are given right now a line which is not a straight line but a curved line, right? Let us say that the total charge on this particular line is Q, but we do not know where exactly that complete charge is distributed. So now we have to find out, for example, the electric field at point P, electric field intensity at point P, where the test charge Q0 is kept, which is at a distance of r from this small element. So we have considered this particular small element over the entire length, where we have assumed that there is a small charge dq and the length of this particular element is dl. So if the entire length of the line is L, then we have considered the length of the element, length of the small current element, or length of the small charge element as dl, and suppose it has a charge of dq, then dq charge is present over a small length dl, then dq by dl should actually be equal to what? It should be equal to lambda, which is your linear charge density, which has been represented here, right? Now if I say dq by dl is lambda, then what should be the value of dq? Dq should be equal to lambda dl. That means if I integrate this from 0 to q, that will actually give you the total charge, then this will be it will be integrated with 0 to L, which is going to be the total length of that particular wire, and that is how we'll find out the total charge present on the entire wire. Then what is the force? A small amount of force due to this small charge at point P. That is going to be equal to what? 1 upon 4 pi epsilon naught Q0, which is this particular charge, into dq, which is this particular charge, over r square into r cap, which is a very simple form of Coulomb's law because the distance is r. Then if we represent this dq in the form of the linear charge density, then we can also write this formula 1 upon 4 pi epsilon naught Q0. dq can be replaced with lambda dl by r square into r cap. This is the net force acting on charge Q0. But then if the net force is this thing, then what's going to be the electric field intensity at that point? It's going to be 1 upon 4 pi epsilon naught. And obviously this Q0 will cancel off because we'll have to divide that with Q0. Remember, we always find out the electric field intensity with respect to the test charge. So we do not have test charge in our formula. So this should only have an integration of lambda dl upon modulus of r square multiplied with r cap, but then this should actually go from 0 to L, or we can just write it as L, which will actually give you the linear charge integral of the length integral of the entire length of that wire, and we can actually have this integration sign over here, and this is going to be L. Do we all understand that thing? So this is how we can find out the electric field intensity due to a linear charge distribution. Now I'm pretty sure that these two are going to be quite easy for you guys. Now the second one we have taken is that we have to find out electric field intensity at point P where a test charge Q0 is kept, which is at a distance of r from a surface. Now rather than a line, now we have a surface. Obviously if there is a surface, we'll also have an area. So we have considered a very small area. This is a small area ds, right? Then dq upon ds should be equal to what? Should be sigma, the surface charge density. We have done this in the last lecture as well. Then dq will be equal to what? dq will be equal to sigma ds. This is going to be the small charge present over that given area. Then the net force is going to be what? Q0 upon 4 pi epsilon naught q sigma ds upon r square into r cap, where it's going to be integrated over the entire surface now. And obviously the electric field intensity will be what? Electric field intensity will be 1 upon 4 pi epsilon naught integral of surface with sigma ds upon r square into r cap. Obviously the q0 will not be there, right? And this will give you the electric field intensity due to that particular area. Similarly, if we talk about the volume charge distribution, now we have considered the point P at a distance r where a test charge is kept Q0, and now we have a surface where we are going to consider a volume. So now I have taken a Q, for example, and a very small volume dV. Similarly, we can write dQ upon dV as what? As gamma. That is how we can, or we can just write rho, for example, which is actually going to represent the volume charge distribution. And from here we can calculate dQ as what? Rho dV. Similarly, the force is going to be what? Q upon 4 pi epsilon naught. The integral of entire volume rho dV upon r square into r cap. And from here we can find out the electric field intensity as what? It's going to be 1 upon 4 pi epsilon naught integral of V over what? Rho dV upon r square into r cap. And this will actually give you the electric field intensity due to a given volume charge. Do we all understand these things? So these are the three volume distributions: the linear charge distribution, the surface charge distribution, and the volume charge distribution. And that is how we can calculate the electric field intensity due to all the three types of elements. Do we all understand that thing? It's a pretty simple part. If you have any problem, as I said, just pause the video, write down everything, or just rewind the video and watch it all over again. Okay? What do we have next? We have the rectangular components of an electric field intensity due to a point charge. So we have considered a test charge at point P here, and the source charge obviously is kept at point Q. Oh, I'm so sorry, I just lost that slide. Okay, so it is kept at point Q right now, O right now, and the test source charge is plus Q, and we have to calculate the electric field intensity at point P. Now I have considered point P in the Cartesian plane having coordinates as x, y, z. That means because intensity is a vector quantity, there will be three different values of intensity in all the three directions. Along the x-axis has been taken as Ex, along y has been taken as Ey, and along z-axis it has been taken as Ez vector. Right? I have considered the position vector of the test charge with respect to the source charge as r vector, which is given by OP vector as xi plus yj plus zk. We already know this, how to represent this, right? We already know this particular point. Also, we can find out the modulus of this particular vector, which is the magnitude, and it will be equal to what? Root over x square plus y square plus z square. This is how we find out the magnitude, which is going to be just represented by r, for example. Rather than writing the entire thing, we can just represent it with r. Now, what's going to be the electric field intensity at point P? Electric field intensity at point P is going to be given by what? 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught multiplied with Q, which is the source charge. Obviously, we do not consider the test charge, upon what? Upon r square multiplied with r cap, which is going to give you the direction along the given vector. Right? So in that particular case, now if we represent these things into their vector notation, this will be what? It will be 1 upon 4 pi epsilon naught into Q upon r square. R square can be written as what? It can be written as x square plus y square plus z square. Obviously, square root will be removed due to the square and multiplied with the unit vector. Now, unit vector is what? Given vector upon the modulus. Given vector upon modulus, that means given vector is going to be r vector, which can be represented as xi plus yj plus zk vector divided by x square plus y square plus z square, which is the magnitude, which will have a square root. That means intensity, general intensity or the net intensity can be represented as 1 upon 4 pi epsilon naught Q multiplied with xi plus yj plus zk divided by what? Divided by x square plus y square plus z square over the power 3 by 2. Obviously a square root and a 1 will make it 3 by 2. This will be the net intensity. This will be the net intensity at point P. But then what will be the value of the intensity at the three different points x, y and z? Then Ex can be written as what? Ex can be written as 1 upon 4 pi epsilon naught into Qx upon x square plus y square plus of z square to the power 3 by 2. How do we calculate this Ex? Obviously I have not mentioned the vector notation. That means this is just the magnitude. So what do? We multiply the vector with the I vector, which is going to be of that along that particular axis, and obviously I dot I is going to be 1. So it will remove the vector form. It will just give you the magnitude of the intensity along the x direction. Similarly, we can find out along y direction, which is going to be what? 1 upon 4 pi epsilon naught Qy upon x square plus of y square plus of z square to the power 3 by 2. Or we can also write this along z axis, which is going to be equal to what? Ez will be 1 upon 4 pi epsilon naught into Qz upon x square plus y square plus z square to the power 3 by 2. And this is how we'll actually find out the intensities along the three directions. Now I have a question for you. Tell me, what if x and y and z are equal? What if all the three coordinates are equal? That means Ex, Ey and Ez should be equal in that case. Therefore, what will happen? Ex will be equal to Ey will be equal to Ez. That means intensity will be same in all the direction, and thus intensity will be spherically symmetrical. It will be spherically symmetrical in that case. If Ex, Ey and Ez are equal, then the intensity will be spherically symmetrical in all the directions because all the three coordinates are going to be the same. Do we all understand that thing? It's a pretty simple concept, guys, as I said, and that is how we can actually find out the rectangular components. If you have any problem, just pause the video or rewind the video and you'll have to understand the entire thing again, but it's going to be pretty easy for you guys. Okay, what do we have next? Next is the physical significance of electric field. What is the physical significance of electric field? So the first thing, it is the characteristic. Let's try and change the color of the ink right now. It is the characteristic of the system of charges and it's independent of the test charge. As I have told you quite significantly, E is given by F over Q, where Q is what? Q is the test charge. That means when we talk about electric field, it does not depend upon the test charge. It will only depend upon the source charge. So it will be independent of the test charge, and it is basically the characteristic of the system of charges, all the source charges which are actually present around the test charge. Similarly, no charged particle experience force due to its own field. So there is a charge, obviously it will have a field, but that field will not have any kind of a force applying on the same charge. So a charge can experience a force due to someone else's electric field, but it will not experience a force due to its own field. Similarly, every charged particle has its field up to infinity. So there is a field around a given charge, but that field can be considered as an infinite field. So every charge will have a field up to infinity, and obviously if another charge is not experiencing a force, that means it is outside that particular field. Then the important point, the direction of the field. This is really important. What is the direction of the field? It's always radially outwards for positive charge. It is always radially outwards for a positive charge, and it's always inwards for a negative charge. That means the field, electric field intensity will always go away from the positive charge, and it will always be towards a negative charge. So it will always go like this. It will always be outside, or it will be always outwards of the positive charge, or will be inwards for a negative charge. So if there is a system of charges of positive and negative, then the field will always go from positive towards negative. It will be outside for positive and inside for negative. And what's the last point, the significance? It helps us to find out what the magnitude and the direction of the force experienced by the charge. So E is going to help you out. If you know the value of E, then we can pretty much write F will be equal to what? E into Q. So it will help us to find out that what is the direction of the force and what is the magnitude of the force. Do we all understand that thing? Pretty simple points. Make sure that you note down all these points, important things. Then the last thing that we have, electric field lines and their properties. So the first thing, electric field lines. What are electric field lines? It is defined as a path, whether the path can be straight or it can be curved as well. Let's try and understand this again. So it is basically a path which can be Either it can be straight or it can be curved. It can be absolutely anything, right? And it is going to be such that the tangent, now this is an important word, such that the tangent to it at any point will give you what? The direction of the electric field intensity at that point. That means if you have any kind of a line, so for example there is a curved line, and if you have to find out the electric field intensity at point P, then what do? I just draw a tangent in this particular direction. If I have to find out here, I'm just going to draw a tangent to this particular line, right? So this is how we are, suppose this is going to be a point here, so I'm going to draw a tangent at that particular point. Obviously the tangent will point out in different directions, which will also give you the variable directions of electric field intensities at different points, right? So it is defined as what? The straight or the curved path, such that the tangent to it will give you the direction of the field intensity at that point. Just as we had discussed in the section before this, for a positive charge the electric field is going to be always outwards, and for a negative charge it will always be inwards. For a system of positive and negative charge, it will always go from positive towards negative. Similarly, for example, if you have to find out intensity at this point, draw a tangent in the forward direction. At this point, draw a tangent in the forward direction. That is how we can actually find out the intensity directions at a given point. Similarly, if both the charges are equal, then what's going to happen? They will have repulsion. That means the field will never converge. They will always diverge from each other. So they will try and go away from each other. They will never intersect, right? So this is what is the concept of electric field lines. That will give you the direction of the electric field intensity at a given point by drawing a tangent at that particular point. Make sure the tangent is always going to be directed from the positive towards the negative direction, right? Never make a tangent this way, because this will be from the negative towards the positive. The correct notation will be always draw a tangent from positive towards negative direction. Do we all understand that thing? It's a pretty simple concept. It's not a difficult concept at all. There is one more thing that needs to be understood in this thing, which is a neutral point. It's going to be an important concept again. What is a neutral point? We all understand neutral, right? Neutral means no effect at that particular point. So suppose there are two charges which are equal. Important thing, if there are two charges which are equal, then the neutral point lies at the center of the line joining the charges. The neutral point lies where? It lies on the center of the line joining the charges. For example, here we have two positive charges. These are the two positive charges. Now suppose this is a straight line, right? Let me just change the color of the ink to make you understand this thing. Okay, let's say green. So for example, if this is the straight line, right, which is joining the charges, let me just draw it again. Straight line joining the charges. Now because we know that both the charges are equal, that means both are positive or both are negative, then the field cannot converge because both are going to experience repulsion. In that case, the field will be, there will be a point, there will be a null point. Neutral point is sometimes also known as null point. Always remember this, right? Null point. So what is the null point? It is the point which is going to be experiencing no field. There will be no field at that point. And how do we calculate the null point or the neutral point for two equal charges? Find out the line joining the charges and the midpoint of that thing. For example, in this situation, point X is lying at the midpoint of the line joining those charges, and that particular point will be acting as the neutral point. There will be no field. There will be zero electric field at that particular point. However, if there are two charges which are unequal, for example, there is a positive charge plus 5 coulomb and there is another positive charge, let's say plus 1 coulomb. We pretty much know that the fields are not gonna converge. They will actually diverge. But in this case, what's gonna happen? The effect of the field of plus 5 charge is gonna be higher because it is having a higher magnitude. That means the null point, rather than being at the midpoint, it will be shifted more towards that charge which will be smaller in magnitude. So for example, in this case, the null point will be somewhere here where the force of the field will be 0 or the net field will be 0 rather than being at the midpoint. So if there are two charges which are unequal, when I say unequal, that means both are going to have different magnitudes. So both are going to be positive or both are going to be negative, but one is going to be having a higher magnitude as compared to the other. So in that particular case, the neutral point will lie more towards that particular charge which is having smaller magnitude. Do we all understand that thing? Simple concept, right? Great. Let's get on to the next thing and the last thing, which is the properties of electric field lines. You have already studied all these points in class 10th as well, right? We have done all these things in class 10th as well. We are just trying to revise that again. So the first property, they start from the positively charged body and end at the negatively charged body. That is what I have told you earlier, right? They are radially outward from positive and radial inwards towards negative. Similarly, no field lines exist inside the charge body. Important point. Inside the body there will be no field, right? There will be no field inside a body. It will always be outside the field. So if there is, for example, we know a magnet, right? A magnet, there is a north pole and the south pole, and the field always goes from north towards south, but they also go from south towards north inside the magnet. That means inside this magnet there is a magnetic field. However, in terms of electric charges, the field will go from positive towards negative. There is a system, then it will go from positive towards negative outside, but there will be no field acting inside this particular object. Right, so make sure you remember this, that there will be no electric field inside this. Therefore, they will not form closed loops. Magnetic lines actually form closed loops, but electric field lines do not form closed loops. Next point, next property, tangent at any point of the EFL. What is EFL? It's electric field line. So the tangent at any point on the EFL will give you what? The direction of the electric field intensity at that point. We have just dealt with this in the previous section right now, right? Similarly, no two EFLs can intersect each other. No two electric field lines will intersect each other. For example, this is an electric field line. Now, how do we find out the direction of the electric field intensity? We just draw a tangent. We just draw a tangent at that particular point, suppose at point P. Now tell me quickly, can there be two tangents at a given point? No, there cannot be two tangents. There can be only one tangent at a given point. So in that case, if there were two lines which were supposed to intersect, suppose this was line 1 and this was line 2 and they were intersecting at point P, then in that case at a single point there will be two different tangents acting. But again, there cannot be two different tangents at a given point. Therefore, no two EFLs can intersect each other. Always remember this point. And the last point, the EFLs are always normal to the surface. That means they will always be perpendicular to the surface. They will never act at an angle to the surface. They will always be perpendicular to a given surface, and that is what is meant by being normal to the given surface. Do we all understand these things? Very simple properties of electric field lines. They have already been dealt with in class 10th. We are just doing a quick revision on that thing. Do we all understand that thing? It's a pretty simple point, guys. Not a difficult thing at all. Now what do we come up to? We come up to the homework assignment. What homework do we have this time? We have 4 questions, 4 simple numericals. What is the first numerical for L2? Lecture 2. 4 charges of the same magnitude and same sign are placed at 4 corners of a square of each side 0.1 meter. What is the electric field intensity at the center of the square? Pretty simple oral question, but you're still supposed to do this thing. Next one, 2 point charges of plus 3 coulomb each are 100 centimeter apart. Then what point on the line joining the charges will the electric field intensity be 0? We have done one similar question in electric charges as well, where the force was asked to be 0. Now the intensity is 0. You have to find out the equilibrium point, right? Third question, a particle of mass m and charge q is released from rest in uniform electric field intensity E. You have to calculate the kinetic energy it retains after moving a distance x between the plates. Simple question, just apply some logic over there. And the last one, 4 particles each having a charge q are placed on the 4 corners A, B, C, D of a regular pentagon A, B, C, D, E. The distance of each corner from the center is A. You have to find out the electric field intensity at the center of the pentagon. There is no charge kept at the last point E. Remember this thing. Okay, so very simple thing, pretty simple homework. Make sure you're gonna do this homework and gonna have these 4 questions done by the next lecture. So guys, this was today's lecture, lecture 2 on electrostatics. Make sure that you have seen the entire thing. Watch it all over again. If you have a problem, do your homework, and I'll see you in the next lecture then. Till then, have a great day ahead, guys. Take care.